Welcome back to another Math and Physics Resource Center tutoring video for SVSU for calc-based physics. So today we're going to be talking about the relationship between force and momentum. So what do we have here? We've got a force versus time graph that's representing the collision of a 58-gram super ball with a wall. And they tell us the initial velocity of the ball is 34 meters per second, pointed directly at the wall, and then it collides and it turns around the other direction. And so I'm just going to call the velocities pointing away from the wall positive, just kind of for consistency. And so I've got negative 34 meters per second pointing into the wall, and then it rebounds with the exact same velocity, but in the opposite direction. And so the one thing we have to relate kind of is how do we relate force and time to velocity? And one way to do that is with impulse, which is actually the change in momentum. And so the thing we know about change in momentum is that it's actually the integral of the force with respect to time. And this is related to another calculus version rate, which is that the force is the rate of change of the momentum with respect to time. So what do we have? So we need to be able to kind of think about force based on this graph and how the momentum changes. So one thing we can start off by just saying is that the change in momentum rate, the final momentum minus the initial momentum, should be basically double the final momentum, and we can talk about why that is. So final momentum minus initial momentum, and I'm going to write this in terms of Newton seconds. So the mass of that block, or that ball, I'm just going to say is 0.058. And so the final momentum, we know again, right, momentum is mass times velocity. So the final momentum, if we multiply those two together, should be 1.972 Newton seconds. And then the exact opposite, right? So it's just opposite signs. So what's actually going to happen is that we got double the initial momentum as a change, because it's the exact same, it's just in the exact opposite direction. So that's our change in momentum right way up here. But how do we relate the force and time to that? So they give us a graph, and if we think about the integral, it's the area, right, under the curve for a force versus time graph. So how are we going to calculate the area? Well, there's two ways, right? We have the shape of this trapezoid, or we can try to break it up. So I'm going to do the trapezoid first, but we could also try to break it up into two triangles and a rectangle if we don't remember the area of a trapezoid formula. But the area of a trapezoid, if I can draw a small trapezoid, is the height times the average of the two bases. So we add up the bases, and we just divide by 2. So in that case, the area is actually F max. Right, that's going to be the height. And then the two bases, well, we've got the top base is 2 plus the base at the bottom, right? So when I say bases, I mean the two parallel sides divided by 2. So I've got 8 divided by 2 is F max. So F max is actually, so 4 times F max is going to be the area underneath the F versus time graph. And then I've got that I know the area rate is still also the impulse to the change in momentum. So F max So 4 times F max is 3.944 Newton seconds. And then if I divide by the 4 seconds from here, from the initial, F max ends up being 0.986 newtons. And the other way to do this, so I'm just going to do, we'll get the exact same answer for the area part, is just to kind of think about breaking this up in another way geometrically. So we get to think about, we've got these two triangles, right? And they're symmetric. They're basically congruent. So we've got two of those triangles, and then we've got the area of the rectangle in the middle. So let's see. So area of a triangle is 1/2 base times height. And area of a rectangle, right, is just length, or length times the width. So the heights for both triangles, right, are going to be F max, and then the base is going to be 2, that distance there. So I'm going to get 2 area of a triangles plus the area of that rectangle added together. So 2 times 1/2, and then the base is 2, and then F max again, right, is the height. So 2 of these, the 2 and the 1/2 cancel, and we're just going to get 2 F max there, plus another 2 from the width, and the height of the box is F max, right? And so we still get that 4 of F max is the same thing as the change in momentum from before. And if we divide this by 4 again, right, we're going to get back to that same final answer. So the crucial thing here, right, is just understanding how the change in momentum is related to force if we have a graph of it, right? Anytime they actually give you a plot of the force, you can always try to calculate the area underneath it. Obviously, right, this is a nice graph because it's very geometrically, it's very easy to break it down geometrically, but sometimes it might not be the case. You might have to kind of approximate and calculate boxes or something like that if the curve is a little bit smoother. But the process is the exact same. You try to calculate the area, and then that should always be for a force versus time graph, and that should always be the change in the momentum of whatever object you care about. So I hope that was helpful, and I guess this is important, right? This actually should be the net force. So you might have interacting forces sometimes, and you'll have to try to account for that, but the same principle applies even if you have to subtract out, say, gravity. I hope that was helpful, and I will see you in another video.